This is Formal Methods, Lecture 3 Recap. The last time we looked at these 4 inference rules that are used for logic proofs. The 4 rules are substitution, Leibniz, equanimity, and transitivity. And then we looked at this example of the substitution inference rule. And with this lecture, we are going to look at the other 3 inference rules and do a little example proof to see how they are used. So let's begin with some exercises that are from the textbook and that are assigned in this course, that are exercises on using Leibniz. So the form of Leibniz is the hypothesis, which is assumed to be true in all states, is x equals y above the horizontal line, and then the conclusion below the horizontal line is expression e with z replaced by x equals expression e with z replaced by y. And so I'm going to give you the solutions to part A of 3 different exercises in the back of the book and let you work through the parts B, C, and D, and etc. So the first question is question 1.7, exercise 1.7 from the text, which is an amazing text, A Logical Approach to Discrete Math. I cannot praise it highly enough. So exercise 1.7 says fill in the missing parts and write down what expression E is. And so we are assuming in here that they're giving us part of a Leibniz inference rule. So at the top we have x equals x plus 2 for the hypothesis, and below the horizontal line we have 4 times x plus y equals, and question mark, and we have to fill in the question mark. So here's the question mark. No. So here's the question. If x equals x plus 2 in all states, then 4x plus y must equal what? So can you figure out what's in the goes in the question mark? So here's the solution. If x equals x plus 2 in all states, then 4 times x plus y must equal 4 times parentheses x plus 2 close parentheses plus y. Now, this part of Leibniz is pretty easy to understand because this is the kind of thing that you plug in when you do algebra problems in college algebra. But it's a little bit more tricky to write down what the expression E is. Do you see? Because Leibniz, below the horizontal line, in Leibniz we have E with z replaced by x equals E with z replaced by y. So E is an expression that has variable z in it. And when you replace z with x, you get 4 times x plus y. And when you replace z with expression y, you get 4 times x plus 2 plus y. So the question is, what is E? See if you can figure this one out. If this is what you came up with, congratulations. E is 4 times z plus y. Now, it's usually easier to check that this is true after you have been given the form of E. Because if E is 4 times z plus y, well, if everywhere there is a z, you replace it with x, then you get 4 times x plus y, which is the left-hand side of the equals below the horizontal inference rule line. And if you replace z with x plus 2, you get 4 times parentheses x plus 2 close parentheses plus y, which is on the right-hand side of the equal sign in the equality below the inference rule horizontal line. And then the rest of the parts B, C, and D are similar. All right, so now here's the next exercise, 1.8. For each of the expressions E was z replaced by x, and hence x equals y below, write the resulting expression E was z replaced by y. And then for part A of this exercise, it's the first row of a little table in the exercise itself, where they're giving us e was 0 replaced by x and hint x equals y. But look, isn't this exactly what they're giving us in exercise 1.7? Because in 1.7, look at part A of 1.7. They give us x equals x plus 2. So they're giving us capital big X equals big Y as the hypothesis of the inference rule. And they're giving us e was 0 replaced by x. They're giving us the left-hand side of the equal sign below the horizontal line of the inference rule in the conclusion part. So they're doing the same thing here. So the easiest way to do this is to write this in the usual Leibniz inference rule format. So if we do that, if we do that, we have this. So here is the solution. Well, it's not quite the solution. Here we have written x equals y as the hypothesis, and we have written x plus y plus w as the left-hand side of the equality in the conclusion. And so don't you see that this is the same kind of exercise as in part 1 exercise 1.7. So what should go now? Can you figure out what goes in the to the right of the equality? In other words, what is e was z replaced by big Y? Well, if x equals b plus c, then x plus y plus w must equal what? b plus c plus y plus w. And now here is the trickier part. What is e? What is the expression e? See if you can figure this one out. I hope you got that. E is z plus y plus w, because if you take z and replace it with uppercase x, which is lowercase x, you get lowercase x plus y plus w. And if you take z and you replace it with b plus c, you get b plus c plus y plus w, which is on the right-hand side of the equality in the conclusion of the inference rule. And then parts b, c, and d are similar. And now the last part of the exercise is trickier yet, I think. So here is the exercise that they give us. They give us e was 0 replaced by x and e was 0 replaced by y. And now we're supposed to come up with the hypothesis. What equals what as the hypothesis of the inference rule. So do you see what so here again, the best way to approach this, I think, is to just write down the Leibniz inference rule with the quantities that they give us. So if you do that, it looks like this. So the solution, so they've given us x plus y times x plus y equals x plus y times y plus x. So the question is, what must equal what in order for these two expressions to be equal to each other? Well, the x plus y is the same. The left hand x plus y is the same in both expressions, but the right hand term, it has an x plus y on the left of the equals, but a y plus x on the right hand side of the equals. So can you see what has to be equal in order for this to be a valid Leibniz inference rule? It's x plus y equals y plus x. And now what do you think the expression e is? See if you can determine what the expression e is for this. I hope you got that e is parentheses x plus y close parentheses times z. And here again you can verify this by taking z replaced by x plus y in the one case and z replaced by y plus x in the other case. Okay, so those are some exercises on Leibniz. Now, the next topic is equality. There are 4 laws of equality that we need to know backward and forward. Well, you don't have to know them in reverse order, but you need to know them back. You need to, at least you need to know them forward. Okay, maybe not backward. All right. So here's the first one. Reflexivity. X equals X. That is the reflexive law of equality. By the way, I always remember this as the acronym RSTL, R-S-T-L. So R for reflexivity, S is for symmetry. Okay, symmetry says that X equals Y equals, parentheses, Y equals X. All right, these are properties of equality that I'm sure you are already familiar with from algebra. You know that 3 equals 4 is the same thing as 4 equals 3. They're both false, right? And 4 equals, yeah, anyway. Or A equals B is the same thing as B equals A. So that's called symmetry. Now the T is transitivity. And transitivity is in the form of an inference rule. And transitivity says that if X equals Y, and remember the comma says means and also Y equals Z, then by transitivity X must equal Z. And here again, I think you know this from algebra. And guess what the fourth one is? 1.5 is the fourth one, I guess. This is from the book. It's our old friend Leibniz. X equals Y on the hypothesis, in the hypothesis of the inference rule. And E was 0 replaced by X equals E was 0 replaced by Y in the conclusion of the inference rule. Now look, this is quite interesting because these 4 laws of equality have 2 properties that are also the inference rule for proofs. Here, let's review what those 4 inference rules for proofs are. Okay, so here are the inference rules for proofs, for logic proofs, and you notice that we have substitution and Leibniz, and so Leibniz was one of the ones that is one of the properties of equality. And then we have equanimity and transitivity was one of the inference rules for equality. So you see these, the 4 inference rules for logic proofs, 2 of them are in common with the 4 properties of equality. Both the inference rules for logic proofs and the properties of equality include Leibniz and transitivity. So those are really basic, very, very basic properties. Okay, so we'll just note that for now. Now, what I want to do now is give you an example of a proof, and this differs a little bit. This example that I'm giving differs a little bit from the one that's in the lecture itself, the main lecture. I think this presentation will demonstrate proof techniques a little bit better than is done in the main lecture. So here's our example proof. Now, check this out. We are going to assume these axioms. Now we're going to number these axioms 1, 2, and 3. So axiom 1 is x times y equals y times x. Axiom 2 is x times x equals x squared. And axiom 3 is x equals x. All right. So we're going to assume that these are axioms, right? And we want to prove this theorem. The theorem that we want to prove is a times b times a equals a squared times b. Now before we get into the details of this, check this out. Do you see this word axiom? And you see this word theorem? Now where have we seen that before? Do you remember this from last time? We said that axiomatic logic systems use inference rules to produce theorems from axioms. So here's our first example of a proof that starts with some axioms and then produces theorems. Okay, in the same way, remember we had an analogy of computational systems where a program processes input and produces output. Well, here we're going to see exactly how these 4 inference rules are used to produce this theorem from these 3 axioms. Okay, so this is an example of axiomatic logic systems. Okay, so let's see how that works. So our 3 axioms are numbered 1, 2, and 3, and the theorem that we're going to prove that and we're going to use the inference rules to prove that this theorem from these axioms. And the theorem that we're going to prove is a times b times a equals a squared times b. Now this is obviously trivial from an algebra math point of view, but the purpose is to illustrate the process by which we use inference rules to produce a theorem from a set of axioms. Okay, so here we go. But the thing that we want to prove is a times b times a equals a squared times b. Okay, so in the proof, what we do is we start with that line. We start with the thing that we're trying to prove, and we try to get it. We try to show that it equals true. So in our proof, we start with a times b times a equals a squared times b. Okay, now here, this is why I've tried to emphasize this outdent and indent and using a hint. Because the first step in this proof is we outdent and say equals, and we indent and we say, and now here's what is in this hint. Now notice this hint says 1. Now what is that 1? That is x times y equals y times x, right? But now look, it's not just 1 by itself, it's 1 with what? It's 1 with x comma y replaced by b comma a. Now that we know how to do textual substitution, suppose I asked you to write down x times y equals y times x. In other words, I asked you to write down axiom number 1 there. With x comma y replaced by b comma a. Well, everywhere there's an x, you would replace it with b, and everywhere there is a y, you would replace it with a. And if you do that, you get b times a equals a times b, right? Is everybody with me on this? Well, look. If b and by the way, how did we do this? We're doing this with substitution. This is the substitution inference rule. Okay, and look. If b times a equals a times b, then what we can do is the b times a in our first line, we can use Leibniz to change that to a times b. So here's what the next line looks like. The next line in the proof. So you see that if we swap the b and the a and make that a and the b, then we have a times b equals a squared, and then we bring down the equals and the a squared times b. Now, I know this seems trivial, but, well, it might seem trivial. But we are formalizing these. We are formalizing this, and that we need to master this. We need to acquire this skill in order to do logic proofs. Okay, later on. And now the next thing that we do is we say, okay, now what is this equal to? Well, so on the next step, what we do is we are going to use axiom 2, which is x times x equals x squared. But look, we don't have any x's in our equation here. What we have are a's and b's. But if we use 2, axiom number 2, with x replaced by a, and if I asked you to do textual substitution with that, what would you say? Well, you'd say, well, that's the same thing as a times a equals a squared. But wait a minute. We have an a times a in this line right above this hint. So what can we do? We can use Leibniz. Okay, and so what is this equal to by Leibniz? It's equal to a squared times b equals a squared times b. Aha, but wait a minute. Does this look familiar? Doesn't this look like axiom number 3? So look, then the last step then is to use axiom 3, but everywhere there is an x, we make it a squared b. And if I asked you to do textual substitution, what would you say? You would say a squared b equals a squared b. So we have shown then that this is true, right? And this little double slash means end of proof. QED sometimes is written as the end of the proof. Sometimes in textbooks they use little squares or rectangles, either solid or hollow, or to indicate the end of the proof. So that little double slash is, it's easy to write when you're doing proofs by hand. or proofs with a pencil or a pen or whatever. All right, so that's true. Now let's analyze this and see exactly where these inference rules are used in each step. Now, this in the first step where we went from a times b times a equals a squared times b, and we use this hint with axiom number 1 to get a times b equals a squared times b, below the hint. We used 1 with x comma y replaced by b comma a. So what we were using there was substitution. You see the form of substitution down at the bottom of the screen here? The bottom of the slide. Substitution is if e is true, then e with 0 replaced by f is true. And so what we're saying here is that if x times y equals y times x is true, then x times y equals y times x is true for x comma y replaced by b comma a. We use substitution to transform an axiom with different variable names to look like the expression that we have that we want to manipulate. So that is inference rule. That is how inference rule substitution is used. All right, so that's substitution. Now the next inference rule that we used in this first step was Leibniz. Now what does Leibniz say? Leibniz says if we have x equals y, if we assume that that's true in all states, then e with 0 replaced by x equals e with 0 replaced by y. Well, look. What we have here is in our hint, we determined that b times a equals a times b. Now do you see that b times a equals a times b? That is the x equals y in Leibniz. Do you see it has that green rectangle around it? So do you see that b times a equals a times b? Okay. Well, if b times a equals a times b, then e with 0 replaced by x is the red rectangle, and e with 0 replaced by y is the blue rectangle. Do you see? So cogitate on this and so you see that this first step of the proof used 2 inference rules. It used substitution to get an expression in the hint to make 2 things be equal to each other, and then it used Leibniz. It used that in Leibniz with Leibniz. Now, I want to make a point now before we go on. You see, the way we use Leibniz in the step of a proof, the format of Leibniz is x equals y. If x equals y is true, then e with 0 replaced by x equals e with 0 replaced by y. So how does that work out as the step of a proof? The way it works out as the step of a proof is that what we have is e with 0 replaced by x on one line of the proof, and then we have in the hint somehow we determine that x equals y, usually using substitution if we need to, and then the line after the hint, below the hint in the proof step, is e with 0 replaced by y. So this shows explicitly how Leibniz is used in the step of a proof. And I encourage you to go back and review this material several times if you need to cement this concept in your mind. And now, before we look at the other 2 proof steps, I want to make a distinction between implicit and explicit proof steps. So substitution and Leibniz are explicit in a proof. You use them directly in each step, and that's what we just did. We just showed how Leibniz and substitution are used directly in each step. Now the other 2 inference rules, equanimity and transitivity, are implicit in a proof. In other words, you don't use them directly, but on the other hand, the validity of the proof depends on both equanimity and transitivity, and I want to show you why that is, and where they they come into play in a logic proof. Okay, so first let's start with equanimity. You see at the bottom of the slide here, what does equanimity say? It says if x is true in all states, and if x equals y, then y is true. If x is true and x equals y, then y is true. Now, how did we use that? Well, what we said here in the first step is we said a times b times a equals a squared times b. If that is true, and then we said, by Leibniz we showed that a times b times a equals a squared times b equals a times b equals a squared times b. So we saw that by Leibniz we saw that the red expression equals the blue expression. Therefore, the blue expression must be true. So that was just kind of implicit. I mean, we didn't have to like manipulate anything to use that. We just did it. Okay, but it depends on this property of equality. Or sorry, it depends on this inference rule, one of the 4 inference rules for logic proofs. And the other one that is implicit is transitivity. Now this slide shows transitivity. Now before we, and what is the transitivity inference rule? If x equals y and y equals z, then x equals z. Now how did we use that? Here's how we used it. In the first step, we showed that the red expression equals the blue expression. And in the second step, we showed that the blue expression equals the green expression. And by transitivity, therefore, what have we shown? That the red expression equals the green expression. In other words, if the first one is equal to the second one, and the second one is equal to the third one, then the first one has to be equal to the third one. You see? So we didn't have to do any transitivity manipulation there. That's how but the structure of the proof depends on it. And furthermore, I don't know if anyone has anticipated this, but we actually used transitivity twice. The conclusion with this transitivity analysis is that the first one equals the third one. But now look, we can carry that, we can use transitivity one more time. Because before we saw that the first one equaled the third one, but now by Leibniz we saw that the third one equals the fourth one. And therefore by transitivity again, the first one equals the fourth one. So we have shown, and that shows that this theorem is true. Now, I know this might seem like, for some students it might seem like this is really difficult, and other students it might seem like this is trivial. It seems like there's always two reactions that students have when they see this material. Some people think it's really, really hard, and some people think it's trivial. The truth is somewhere in between, probably. I don't know. But if it's difficult for you, just keep going over it again. And if it's trivial for you, well, good for you. But bear with us. You know, it's the basis of all logic of all logic systems. Okay, these are just very basic concepts. Okay, and that concludes our recap for lecture 3. Even though it wasn't much of a recap, it was I think there was a lot of new material in here, or some new material anyway. All right, so good deal. See you next time.